A strange thing is happening in technology right now. Our computers are getting smaller, but the machines required to build them are becoming enormous. Hidden inside that contradiction is one of the most important stories in modern tech. Somewhere in Taiwan, right now, a machine is running. It hasn't stopped in days. It fires a laser 50,000 times per second. Each shot lasts 1 trillionth of a second, and every single one of those shots is what makes modern chips possible. Most creators think the global artificial intelligence race is won by designing smarter software or buying faster GPUs. They are completely wrong. The real bottleneck isn't compute, it's light. Almost the entire modern world depends on one company to control this bottleneck, ASML, a Dutch company building a machine called an EUV scanner. It is the most complex commercial manufacturing tool ever assembled by human hands. To print advanced transistors onto silicon, it must drop liquid tin into a total vacuum and blast it with a massive carbon dioxide laser. The tin instantly vaporizes, exploding into a searing, microscopic cloud of plasma, emitting a brief invisible flash of 13.5 nanometer light. That tiny flash of light is the only reason the cutting-edge processors running GPT, Gemini, or Claude even exist. Yet, for all of this extreme complexity, the process is catastrophically inefficient. Only a microscopic fraction of the energy ever reaches the wafer, with wall plug efficiency plunging below 0.1%. And now, it is hitting a hard wall. Physics has a strict rule. The size of the features you can print is fundamentally tied to the wavelength of your light. Shorter wavelength means smaller features, but at 2 nanometers and below, something strange starts happening. You are no longer dealing with clean engineering. You are dealing with statistical probability. At these extreme boundaries, there are literally not enough photons hitting the silicon wafer consistently enough to print a perfect line. Imagine trying to spray paint a flawless line 1 nanometer wide, but some of the paint particles randomly decide not to show up. At normal scales, that doesn't matter. At 2 nanometers, a single misplaced photon can destroy an entire transistor. This is called shot noise, and it is the fundamental barrier threatening to halt human advancement. To survive, the semiconductor industry has to make a radical, terrifying choice. They have to abandon traditional lasers altogether and rebuild chip manufacturing around massive particle accelerators. Under option 1, America, via a company called xLight, is attempting compact reduction. They are trying to shrink accelerator physics small enough to fit inside a regular commercial cleanroom. Traditional lasers use atoms, but a free electron laser skips the atoms entirely. By shooting a beam of electrons at close to the speed of light through a long magnetic structure, the magnets force the electrons to zigzag. When charged particles change direction at near light speeds, they emit light. The electrons synchronize into tight bunches, generating an EUV beam that completely eliminates the need for exploding tin. But accelerating electrons to near light speed eats up an alarming amount of electricity. That is where Japan's gamble comes in under marker 2. Japan decided size isn't the problem, power efficiency is. Their design, called an energy recovery LINAC, loops the electrons back through the machine. As they slow down, they give their remaining energy back into the accelerator, acting like subatomic regenerative braking. The result is a massive, continuous 10 kilowatt stream of extreme light, powering 12 factory scanners simultaneously, compared to the 500 watts of current ASML tools. Then there is China, severely cut off from purchasing ASML's most advanced machines by strict Western export restrictions. Beijing didn't try to shrink the technology. They scaled it up unconditionally. At Tsinghua University, researchers are designing a massive circular storage ring, 150 meters across. Using steady-state microbunching, they circulate electrons continuously inside the ring at near light speeds. One laser organizes those electrons into tight, synchronized bunches, emitting powerful, continuous EUV light to supply an entire grid of scanners simultaneously. For China, this isn't a simple technology upgrade. It is an absolute declaration of technological independence. And if you want to understand exactly how China is trying to replace foreign chips in that fight, I made a full video on that. Link is in the description. This global race exposes an incredible, beautiful paradox. For 60 years, the entire technology industry has been obsessed with miniaturization, making things smaller, sleeker, more portable. Yet printing the smallest structures on Earth now requires building some of the largest, most expensive machines humanity has ever constructed. Billion-dollar instruments originally designed to study the Big Bang are being repurposed to carve the atomic brains of modern computers. Here is the uncomfortable reality. ASML looked at free electron lasers years ago, ran the numbers, and explicitly chose to keep using exploding tin. Why? Because in mass manufacturing, Elegant physics means nothing without uptime. A fab must run 24 hours a day, every single day. A single hour of failure costs millions. ASML's machines already work reliably on the floor, and the entire global ecosystem is built around them. History is full of technologies that were technically superior, but commercially too late. ASML will continue to dominate the immediate present, but the boundary of progress has officially moved. The future no longer belongs to who can design the smartest software. It belongs to whoever controls light.